Hello and welcome to our second video in our series on Birth of a Synth, which is all about my attempt to build from scratch a polyphonic analog synthesizer. This is where we left it in the first video, with this kind of block diagram of just some of the main components that we're going to need. We know we're going to need some kind of interface where all the knobs and buttons and things you would find on a synthesizer. We know we need an analog engine for actually generating the synth sounds, and then a microcontroller and some other ancillaries to tie it all together. So let's move on from this kind of block diagram and start thinking about how or what kind of elements we're actually going to need to create. So fundamentally, what we're going to be designing initially is something like this. So this is it's actually a synthesizer, but this is a printed circuit board. So we have the green printed circuit board at the bottom there. See if I can make it a bit bigger. And we have all of our controls. This also has some analog electronics on it. You can see the different components. So fundamentally, this is what we're going to have to create. We're going to have to create a printed circuit board which holds all of our interface controls. So all of the potentiometers that we see here and the knobs and the switches. We're going to need to create a second printed circuit board which will fix underneath that, which will have all of the analog electronics, because I think unlike this board here, I'm not going to be able to fit all of my analog electronics on. I'm going to have 12 voices and 2 oscillators per voice. Is going to be quite a lot of chips I'm going to need to use. So we're going to have 2 PCBs, but fundamentally it's going to look a bit similar-ish to this. So the question is, how are we going to create a printed circuit board like that? Well, the answer is by using a tool, and I use a tool called Kicad. I'm currently on version 7. Kicad is a tool which enables us to design and create the layouts for printed circuit boards from scratch to being able to output the files for getting a printed circuit board made by a manufacturer. So if we have a quick look, this is a scoreboard project that I've been working on. This is our schematic. So this is a electrical diagram which basically specifies all of the components that we want to use and how they're all wired together. Then there's a process which we assign these individual components with a physical component, the actual physical component we're going to use. Then there is a third step, which is physically laying out on a physical representation where all of the components sit and how they're all wired together with these wires or traces. So we're going to use Kicad to get to this point here. This point here, we'll be able to output some design files. We can then get those, get the PCBs made by a printed circuit board manufacturer. I can put some of the components on it. We can see if it works. So this is the point that we're trying to get to. So I've used Kicad for a number of years. It's a free tool. Doesn't have all the bells and whistles of some of the commercial products, but the commercial products are outrageously expensive. This free tool is perfectly adequate for what I need to do with it, and it's going to be perfectly adequate for this project. So that's the tool we're going to use. The second thing that we need to think about is the microcontroller. So if we look back at our diagram, one of the most important blocks is this microcontroller block in the middle, which ties together our interface and our analog engine. So we need to choose a microcontroller for the project, and I have a pre-selected one. I am going to be using a ST manufactured STM32H7 microcontroller. Now this, in the grand scheme of things, is actually quite a powerful microcontroller. It is an ARM design. It's a Cortex M7 design, and it's pretty much the fastest Cortex M7 that you can get, because you can clock it up to 550 megahertz, which is really quite quick. It's got a megabyte of flash memory. The flash memory is the memory that holds the code that we're going to write, and half a megabyte of RAM. So this is going to be more than sufficient for everything that we need to do. It has the ability to do all the peripherals that we need to do, and we'll go into that in a lot more detail. So you could argue that this is probably massively overkill, but I'm going to start with this. This is a microcontroller that I've used many times before. I know how to use it. I know how to program it. I know how to wire it all up. So it's a fairly risk-free solution. They're not overly expensive in the grand scheme of things. And we're going to go with this one. So that is the microcontroller. The second element then is the analog engine here. What are we going to use to create this analog engine? So lots and lots of different ways we can do this. We could create all of the analog circuitry from scratch. There are manufacturers who supply integrated circuit for particular elements of this. So you can get oscillator chips, you can get filter chips, voltage controlled amplifier chips, and some of the big polysynths that are around or have been around for a long time have used some of these to great effect. I have decided that because I want to try and keep this project as simple as possible, I'm going to use a chip called an AS3394. And again, this is actually something I've used in the past. This is a chip which combines some of the elements that we need in order to get our analog synthesizer behavior working. It has a voltage controlled oscillator within it. It has a voltage controlled filter, 4-pole filter within it, and it has a VCA in it, and it is voltage controlled, which means that we can change the behavior of the analog engine by using voltages. So we can connect this to our microcontroller. A microcontroller can give voltages to this, which will select what waveforms we want, what pitch we want, what filter settings we want, what settings on the VCA, how loud it is, and it will produce the waveform at the end of it. So this will do the majority of the work that we need in order to generate our analog audio. Now, because I said in my specifications that I wanted 12 analog voices of 2 oscillators per voice, we are going to use 24 of these AS3394s, and they will be on our secondary printed circuit board and will be controlled by the microcontroller. So we know the Kicad design package that we're going to use to design our printed circuit board. We know the microcontroller that we're going to use. And actually, if you look at this one here on our Dart scorer schematic, this is actually a H7, STM32H7, which is the same chip. So I've already got some of the kind of layout done, so I can make use of work which I've already done. And we know the analog chip that's going to drive the majority of what we need to do on the analog side. Obviously, there has to be a lot of analog circuitry around these chips as well. You do need stuff to help drive it, to help make it all work. We're going to have to think about power supplies and other bits and pieces. But fundamentally, that's the decisions made on the building, the basic building blocks. And now we need to fill in all the details around this. So the other piece of software that we're going to use as well, it's going to feature prominently in the project, is STM32Cube IDE. Now this is a programming tool which is provided by ST, the manufacturers of the microcontroller that we're going to use. Sorry, I have the wrong version of that. Right, there is a bit of an issue with this. I upgraded to 1.8.0, which is the latest and greatest, and I found lots of problems with it. So I've gone back to using version 1.14.1, which I know is stable. I've worked with for a long time. So let me just launch this. This is going to open up the integrated development environment, which is where we're going to do all the programming for the STM32 chip. This is a really interesting tool because one of the main features in it is the ability for us to configure the chip. It's just opening up now. It's called the IOC. And it's taking a little while. Come on, you can do it. Yes, there we go. So this is a representation of the chip that we're using, the STM32H7. and basically we can attach things to all the little pins all around the edges. Well, that's what we're going to need to do. These pins are what are going to control our analog elements. It's on these pins as well that we shall attach all of our controls so that the microcontroller knows the settings of our potentiometers and switches and everything else. It's also where we're going to attach our MIDI, where we're going to attach our EEPROM, which is a device that I'm going to use for persisting presets, where we're going to attach the USB connections, etc., etc. So this is the brain, and this tool here allows us to configure all of the functionality of the chip, all of the pins. So what I would generally do when I'm working on a project like this is to work in tandem between STM32Cube IDE and my schematic in Kicad. Or I say Kicad. I don't know whether other people say Kicad. I would say Kicad. So work in partnership, because only certain pins have the ability to work with certain peripherals. So we need to make sure that we're selecting the correct pins in this tool here, and then making sure that we use those pins within our design. So these pins here are a representation on the schematic of the pins in this diagram here. So we just need to make sure that we're marrying the two up, and we're using all the correct pins for everything. So you'll see as I go along, there'll be quite a lot of cross-referencing between here and Kicad as we're wiring up the microcontroller to sit as the heart of the synthesizer, talking to all the external components. So what I'm going to do, let's close all this down, and I am going to create a new Kicad project. I have a... Okay, so I'm going to create a new folder in here, and I'm going to call it hardware. And within our hardware, we're going to have a front printed circuit board and a back printed circuit board. The front printed circuit board will have all of the controls on it, and probably the microprocessor, and probably the power supply and all the power filtering and etc. And the back board will have all of the analog electronics for the generation of the actual synthesized sound. So I'm just going to call this front. I'll create another one for back. We won't use it yet, but it'll be there for when we do want to use it. And I'll go into front, and I will call this, let's call it Birth of a Synth Front. We don't want a new folder because we've already got a folder. So there we are, and I can open up schematic, and it's completely empty. So the first thing I'm going to do is just go into the page settings and make this page a bit bigger. Now, what I'm thinking is I might actually design the entire synthesizer in here, in the front, and then what I will do is I will split it up, and I will take the elements that I want to put on the rear printed circuit board. I'll cut them out of here and paste them into another project, and then we will define the interface between them, because that front printed circuit board will need to talk to the back printed circuit board. So there's going to have to be some kind of physical connectors which connects those together, and we need to make sure that the interface between the front and the back is the same on both. So the pin that we say for 3.3 volts power supply, for example, matches up to the 3.3 volt power supply pin on the rear. So, but I think it's easier for now just to design the whole synthesizer in one schematic, and then we can look at splitting it up. So let's get into that. Okay, so the other thing we will do is I will close down STM32Cube IDE, and I will create a new folder in here. So not hardware, but firmware. If I can spell it correctly, firmware. And what I'm going to do is create a Birth of a Synth workspace. It's just an empty folder. I'll go back and open up the correct version, 1.14.1. We will browse to Birth of a Synth, Firmware, Workspace. We'll launch this, and I will create a new project in here. So when we create a project, we need to specify the chipset that we're going to be working with. So I need to start new project. It's just downloading the latest information about all the latest chips, etc., which are available. Always does this every time you open it up because they're constantly releasing new products. So it's just to make sure you've got everything up to date. Whilst we're doing that, I need to make sure that I select the correct chip. So we are going to be using need to get this correct. I believe it's a ZG. Let's just have a little look. Let's open up Kicad. Let's go back into the Explorer project that I've been working. It is a ZG, so 723ZG. So if we go to the selector, once it loads, here we are. So we can type in the part number here. So it's STM32H723Z. Sorry. The wrong box, this box, and it's a ZG. Double check, ZG. So it's one of these, and it's the ZGT. So we'll go next, and we need to name the project. I'm going to name the project Birth of a Synth Firmware. We're going to use C, and we're going to use the STM32 cube, which is what I showed you earlier. Yeah, and we'll go and we'll create that project. So while that is generating, we'll go back to Kicad, and we'll go back to the project. So this is the front. Remember I said, oh, here we are, it's actually loaded up. So you can see in our project we've got the STM32H723, and none of the pins are attached to anything, which is exactly what we want. So we will go back to here. So the first thing I'm going to do is I'm going to put in place, in the diagram, in the schematic rather, is our chip. Now, as I said to you before, I have worked with this chip before, and I actually have an implementation here. And I can copy this entire thing like this into here, and then I can take you through it. So we've put it in a little box here. If you notice, there's no wires connecting this with any other components. You look in the dart scorer schematic, there's no wires. The way this is connected together is by these labels. So this pin is labeled a button function for debounced. If I copy that text and search for it, you'll find the other end. The other end is here, attached to this component. So in essence, that is a wire or a connection between here and the microcontroller. We just don't have to draw it on and get a really, really messy diagram. We can use labels to connect them. So I can now close that down. So the first thing I'm going to do, before I explain all this stuff up here, I'm going to go and remove all of these labels, because this is from my old project. We don't need any of these. These crosses mean that there's no connection on that pin. So let's go through and delete them all. I'll delete all the crosses as well, because we don't know what pins we're going to need. Let's have a nice clean implementation to start with. Almost there, so last few, and the same on this side. I'm sure there's an easy way of doing this, but it works. I'm just using my mouse wheel to scroll in and out, and depending on where the mouse is, that's where it scrolls in and out. So if I put my mouse here and scroll in and out at that point, quite clever really. Right, okay, so that's where we can stop. So there's a few standard settings or a few standard connections that these microcontrollers always need to have. Now, bizarrely enough, if I look in the STM32H723 diagram, datasheet, and I go to the power strategy, where is it? Power supply scheme, it's here, but it doesn't tell us what we should be connecting to these pins. So VDD is our power, VSS is our ground. Well, there's a couple of other things we need to connect, like VCAP and some other bits and pieces. It doesn't tell us what we should be doing with them. If I look in the datasheet for a very, very similar microcontroller called the H742, which is pin compatible, in the same diagram, it tells us exactly what we need to do. So as you can see, if I scroll in a little bit on here, we need to have some capacitors on our power supplies. And we need to have 100 NF capacitors and then a 4.7 capacitor on all of our power connectors. So if we go back to the schematic, apologies, back to the schematic, you can see here's all of our power connectors. It's actually got quite a lot. They all take the same voltage, which is 3.3 volts, and they all need a 100 nanofarad capacitor to ground. And the purpose of this is to try and smooth that input voltage. Any spikes, voltage spikes that come through, rather than go into the microcontroller, will hopefully be filtered through these capacitors, because capacitors will pass through alternating current, and then down to ground. So what I have copied across and going to reuse is every one of these pins has a connection to plus 3.3 volts. We haven't yet defined where that power is coming from. We'll do that a little bit later on. It's enough now that we've got a label with 3.3 volts, and they've all got a 100 nanofarad capacitor. And then if we look back at the data sheet, we also need a couple more. We need a 4.7 capacitor on there as well. V battery needs to be connected to 3.3 volts. VDDA is our analog voltage, so this is the voltage which will drive the the analog to digital conversion elements of the chip. So you can see here the analog domain, and again these need to be filtered with 100 nanofarads. So we've also got that. I keep opening this, don't I? Also have that. So VDDA, we have two capacitors to ground. The USB one has capacitor to ground, and then we have our 4.7 on one of the pins. So we've wired it up as per the specifications. That's great. Right, so then we've got a couple of other bits and pieces. We've got this NRST pin. That is a reset pin. And the reset pin is used by our debugging probe, which we're going to use to connect between our computer, where I write all the firmware, and the microcontroller on our printed circuit board. I am using ST-Link version 3. So let's just find that and I'll show you it. You'll see this in later videos. ST-Link version 3. It's basically a little piece of plastic with a couple of connectors. One of them is a USB into your computer, and then the other one is a connector onto a header on your board, which is connected to I chose the worst possible image there. Let's have a look in here. There we go. It's basically one of these. And then one of these connects to a little pin header on your board, which we're going to add, and that enables you to program the chip and also to debug the chip, so you can run it in real time and figure out what's going on if you're having any problems with it. So let's go back to here, and one of the pins that is required is this reset pin, because the debugger, the programmer, needs to reset the chip when it tries to flash the code down into it. This is the power management system. You can turn it on and off by either pulling it to 3.3 volts or to ground. We want it on 3.3 volts. Right, here's another little thing which we haven't mentioned before, the boot pin. So the boot pin, normally this would be attached to ground, and that means that on startup this would look in its own internal flash memory to find the program to run. That's normally fine, but I want to do USB firmware updates. If you remember from our specification, updating firmware over USB, so that when I make changes to the firmware, extend it, fix bugs, put new features in, I want to be able to flash it into my sequencer synthesizer over USB. So there's a label here called boot helper level. I'll explain that later. But it also has a 10k resistor to ground, so it's pulled down to ground, but we can pull it up to 3v3, at which point it will then look on the USB port, and that's how you do the updates. We have a couple of timing capacitors which we need to put 4.7 capacitors on, and again that is in the data sheet. VCAP. Oops, I keep opening that. There is a reference voltage used by the analog to digital converter. Again, it's 3.3 volts and it's filtered with 2 capacitors. Again, this is all from the data sheet. It's standard stuff. Every time you use one of these, set it up exactly the same. Hence why I was able just to copy and paste it from the previous project. And then we're going to use a crystal. And there's a 24 megahertz crystal here. And that has to have some capacitors. And that's attached to the PHO and PH1 pin. And that's all really standard stuff. So as I said to you, I'm going to try and keep this in sync with the STM32Cube IDE. So all of the power pins are already marked here, so we don't need to do anything with that. But this doesn't know if we have a crystal connected to it or not. So I'm going to go into System Core. I'm going to go into RCC, which is our clock. I'm going to say high-speed clock is a crystal resonator. And now, if we zoom in here, you can see that PH0 is our crystal in, and PH1 is our crystal out. And we just make sure, yes, PH0 and PH1 are connected to the crystal. So that's fine. Right, so that's the kind of default setup that you always need to do if you want to work with one of these chips. It's just to get it powered up, make sure the power supplies are all filtered. And I'm going to do one other thing in this video before we take a break. And that is the pin header for our ST-Link debugger programmer. And again, I'm going to take that straight from project. We have somewhere in here. Here we go. Main MCU connector. I'll take the whole thing because I like in these little boxes. Nice and neat. And let's paste this up into here. We can move all this around at a later date. So this is the header that we need. The connections are to power and ground, and then also it has 3 additional connections. One is to the reset pin, one is to the I/O, the data I/O, and one is to the clock. So these are the 2 pins which really connect you into your PC and allow you to flash data programs into the memory of the microcontroller and also to debug it. And then they have the reset pin, which they need to do some reset during the whole process. So what we need to do, we've already got this pin connected. I'll take a copy of that label. Go here, and you can see we've already connected this label to the reset pin, so we don't need to do that. We just need to connect up these other two, the I/O, input output, and the clock. So if we go back to our STM32 tool, I will go into System Core again. No, it's actually moved, sorry. It's in Trace and Debug. So if we look in the Trace and Debug menu, Debug, Debugger, I'm using a serial wire. Click on serial wire, and it assigns 2 pins for SWDIO and SW clock. And they are these pins here. This is quite handy. If you click on the configuration of the pins, you can see they highlight on the map here. One thing I always like to do is if you right click on these, you can pin it. And pinning means that no other operation will overwrite it. Sometimes if there's conflicts and you try and set one of these pins to something else, it may jostle these around and things. I don't want anything moved. I want it exactly where it is now. So the I/O is on pin PA13. So I/O, this one here, needs to go to PA13. PA13, PA13. And the clock one needs to go, that's this one here, PA14. So we'll come up here, we'll take the clock, it's PA14. And that's it, we're done. So this schematic now represents the microcontroller. We've got a microcontroller here, and we have a header, so a little pin header, which will be on the board, which we can connect our debugging probe to. And this connects via these labels to the microcontroller. The microcontroller is fully powered and to ground. All the little bits and pieces that we needed to add in, crystal, filtering for the voltage reference for the analog to digital converter, it's all done. So if I was to have this made up now, this would be a working microcontroller that we could connect to our PC and program. So that's the starting point. And if we go back to our block diagram, we've now got in place in our schematic this microcontroller. That's the kind of heart of the system. So there's some other bits and pieces that we need to do in order to get the boot working correctly, the boot mode working correctly, so that we can do the USB updates. But I'll leave that for the next video. So thanks for watching. If you have any comments, put them in there. If you find it useful, let me know. If you think it's dreadful and I'm not explaining things very well, let me know. And I'll see you in the next video. Cheerio.